that there is, I think, one code, and I would say it was already there when I started my PhD back in 2010. So it's a very old SPH code, and
right, yeah.
And I know actually people that would be interested because it's something that they are not spending time on. Like they would like to make some blood simulation, some stuff like that. But blood simulation on top of other stuff that are actually the focus of their simulation, but they'd like to have also some blood. So it's people that are actually interested but not spending time on. I'm thinking about some companies, for instance, where they were actually using, but it's also because that's super efficient particle simulation, like the one from Flex. Guys, the guys from the Insimo company, that's actually what they did. They implemented. I mean, they are implementing with so far. They are all solid mechanics simulation, but when they need blood simulation, morning Jonico, they are adding flex particles on top of that. So that's actually what they are doing. But that's the kind of SPH or particle-like simulation I heard from a long time. I was thinking about you, Jonico, because obviously meshless approaches. It's actually something Jean Nicolas looked at at the very beginning of his PhD, so 3 years ago now, even maybe a bit more, because it's sometime you ended your PhD also now. So yeah, that's
we all met as students and now we're all doctors.
Exactly.
I didn't get what you said. Sorry, Annika.
We all met whilst we were still students, and now we're all doctors.
Cool. And and so I don't. Can you just say a few words about this SPH code, Jean-Nico?
About which SPH code?
The one you developed. It was ML.
Because SPH is quite large. It can do fluids, but it can also do elastic behaviors. I mean, it's an interpolation scheme. So in my case, I did. I tried to solve the Galerkin approach with SPH in the case of elastic materials. So the same thing as we are doing with the standard element. I tried to do it with particles, so with point clouds. I tried SPH, so the SPH approach for the shape functions, and also a kind of integral approach with SPH, where you try to approximate the volume taken by a particle, and you integrate the Galerkin equations using this approximation. We did this, like Hugo said, a long time ago. It was something that I don't know if you know Müller. Matthias Müller did a lot at 20 years ago, and it works well for computer graphics domain, but not so much when you want a lot of accuracy, like we did. So. Yeah, we kind of swapped. We stayed with meshless a little bit longer, but swapped to MLS approach, moving least square approximation scheme, which gave a little bit better result, and also used the background grid for the integration. So, but yeah, I mean, we did play with SPH, but not for fluid.
So you're actually doing SPH for solids, mostly, right? Okay, So the SPH that I've been working with, I specifically targeted the fastest available one, which was a guy in the US. What's it called again? He worked with NVIDIA at the time, but he's now in one of the universities, produced a code which he called Fluids version 3, which had improved the speed of the sorting and think still is the fastest SPH code. So if you want a simulation that has a lot of particles in it, it's preferable under those circumstances. But it's a single GPU code that would run 1 million particles on a single Tesla GPU. And then I was wanting to get the kind of fibroelastic behavior that you find in anatomical tissue. What I've been doing is I've basically added a network of springs between particles in order to produce that. So it's in terms of physics, it
means you are having both a mass spring model and a SPH model on top of that, or?
Yes. So essentially, each particle has 3 outgoing springs. It can have as many as you like. If you create a regular grid and you have 6 outgoing springs, then it's relatively easy to say, oh, I want a particular anisotropy because however, what I'm actually doing is I'm doing it with just 3 outgoing springs per particle, because what I'm wanting to do is tissue remodeling. So essentially, I'm rather strongly using the analogy that the springs are the fibers in the tissue and the SPH fluid is the matrix of the tissue. Mm-hmm. And then in order to have the tissue remodeling, what I actually do is I say that I have chemical diffusion between particles, which I use for the morphogens, which are the hormones which control the behavior of the genome of the cells. I have a genome and I have epigenetic state for each particle, and the intention is that I will then be able to have a morphogenesis simulator that will start from a zygote and grow a segmented body, grow limbs and muscles and tendons and so on. One of the key things is mechanical remodeling, which is to say that for each of the springs, we have a parameter accumulating strain and strain squared over a sort of limited time window, and those are then used as the mechanical stimulus to remodeling for lengthening, shortening, and strengthening and weakening of tissues. And I have one kernel which goes around and adjusts the length and strength of springs, and then when they reach a given limit, they then either duplicate or remove a particle in order to grow or shrink the tissue. Now, one of the interesting things which came up was that the Fluids version 3 code used the 6th order polynomial smoothing kernel, which was very fast, which is obviously what they were focused on, and it was reasonably stable for the simulations that they were doing. As soon as I started adding springs, I started getting the clumping instability, which can occur with certain types of smoothing kernel in SPH. So I had to change over to the Wendland smoothing kernels, which are the ones which are actually defined in terms of not causing the clumping, and it relates to the Fourier transform of the kernel and whether or not there are basically places. I should have come with the presentation. I can't do this very well off the cuff, but it's essentially most of the kernels which people use intuitively tend to have Fourier transforms which go positive and negative, and this allows under certain circumstances that particles can clump together,
Is this because of the derivative? Like, with a certain shape function, if the derivative is not well aligned, then as you get closer to a particle, it can actually repulse you. Since we work with gradient of displacement.
Yes, yeah.
Okay, this is what
I can dig out the papers for you so that you can read it. I think that you are much better trained in the mathematics than I am. I've had to sort of teach myself by reading up.
Nick, I just need to get just so that you know, I'm getting back. Christian told us when he registered to the STC that he wanted to talk about the shells. It's going to be 10 minutes, not more, I guess, because it's super short. It's just a one-to-one discussion. Then I'll get back here, okay? Just so that you know, I'll get back, especially to plan a bit this SPH plugin development, how to manage that and so on. Okay.
Yep. Okay.
I'll get back in a second, in a minute, I would say. See.
Yeah. Jean-Nico.
Yes.
I understand you're moving back to Canada soon. Is this because you've now finished your PhD?
Yeah, I finished, but it's also because now I have two kids.
Yes.
And I'm quite far from my family, so I will get back close to them.
Yes.
Yeah. That's the main reason.
Yeah. So are you in Quebec or?
Hey, I'm in Montreal.
In Montreal, right? Okay.
Yeah.
And will you still be connected to the SOFA community, or will work take you away?
No, work will. I mean, obviously I want to stay connected, but it will be on my free time.
Right.
So yeah, not for the work, but
right.
Yeah, I'm still hoping to always keep like a foot in the research domain, especially what I did for my PhD.
Yes.
But yeah, we'll see.
Yeah. So, is your work at all connected with your research?
Nope.
Or,
it's a finite element, but not for fluids and not for elastic bodies. It will be for electrical currents and the whole new domain. But
new domain, yes, right, fair enough.
Yeah.
No, I'm coming to the end of my postdoc. So in July, I catch the plane and I fly back to Europe. And
because where are you now? For your
I'm currently in Australia.
Oh, in the where?
in Brisbane.
Okay, not in part with the team of Adam, right?
No,
do you know Adam Vitek?
No, I don't.
He works a lot with meshless methods. He's in Perth.
What's Adam's surname?
It's Adam Vitek and Carol Miller.
He's in Perth.
What?
He's in Perth.
Yeah, Perth. Yeah, and they work a lot with meshless methods.
I'm sorry, Nick. Where are you in Brisbane? Are you at CSIRO?
Yes, I am. Yes.
Ah, okay. I did an internship there about 10 years ago.
10 years ago. Okay,
Yeah.
no, I haven't been there that long. I started in 2018.
Oh, okay, great. So it was before my PhD, actually.
Right. Okay. Yeah. So I'm with the robotics group, who are they're not in the center of town. They're kind of they're north of the river. In Brisbane and sort of westward inland, so we're sort of in that direction. We're near the edge of the city.
Okay,
but yeah,
quite a large city, by the way.
Yeah, it's 2 million people. So I think it's the third largest city in Australia. But Australia is basically about 5 city-states sitting on the edge of a continent, and the continent is almost empty.
Mm.
Yeah.
I had a good time there.
All right. Yeah. Getting back to what I'm actually doing is that yeah, I've got this morphogenesis code, and the idea is that having springs in a smooth particle code should be able to produce the kind of fibrous elasticity that we see a lot of in the body, and then the morphogenetic growth. It's kind of it's a research area in itself because you have the biologists doing it, and then you have people doing evolutionary robotics who want to create soft robots. And there's a question, well, so how do you parameterize it so that you actually get robots that work instead of just a mess? And my input to that was that they should actually study some more biology and copy what actually happens in the biology. And then I'm also working on computer vision, visual tactile interaction. So during my PhD, I sort of produced the outline of how to do visual tactile fusion using algorithms from monocular SLAM and from shape from shading to track a visible surface. And I saw that the way those algorithms were structured, it should be possible then to actually fit a physical model under the surface and have that physical model predict the expected movement. And basically you would, through interaction, learn the structure and material properties of an object. And that this would eventually be, for example, a way that you can capture anatomy from dissection. You would put strain gauges on the anatomist instruments and binocular video recording of him performing the dissection, and you should be able to basically capture the topology and the material properties of all of the tissues, so that you then have an anatomical model that's actually justified from sensor data rather than from expert opinion. Jean-Nico, I think you're muted.
Yeah, thank you. Starting from an initial object, or I guess from an initial model, or are you building this model using only
so the idea is that it should be possible to bootstrap without a pre-existing model,
okay.
but that yes, in a lot of interactions, you would want to use all the prior information that you had acquired in the form of models of objects that you had handled, because you don't want to start from scratch every single time, but you need to be able to do so the first time.
Oh, okay. So you I guess you detect different. So you have a lot of computer vision, I guess, to differentiate the different objects that you see.
So start with what's known as monocular passive dense visual SLAM. So it's basically if you can take a single webcam and wave it around. I will try turning on my video here, so at least you can see my hand gestures.
Yeah.
Allow. Here we go. Oopsie, you can see it's dark over here. Start sharing. Oof. Okay. Hi.
Okay. I got you.
Glasses off. And so if you can wave a camera around, then you have parallax motion in the image, and that gives you a very good cue for depth, and that's the basis of monocular SLAM. Is that it estimates the trajectory of the camera relative to the depth map that it gradually refines and improves. And then shape from shading says that if you have an illumination model and you have you model the scene as a reflectance map as well as a depth map and a model of where the illumination sources are, then you can understand when materials are specular, when they're shiny, and
occlusion, I guess. Like
well, yeah, occlusion. Hang on, I'm going to turn off those ceiling lights there because I think they're spoiling the video here.
Okay.
Yeah. How would I put it? The yeah, occlusion is reasonably well dealt with. The bigger issue is that the most of the monocular SLAM algorithms depend on what's known as the rigid world hypothesis, which is to say they expect that nothing in the scene moves except for the camera, which of course isn't true in most useful real scenes. However, the regularization which is used in the depth map is it's basically edge preserving regularization that says that most adjacent points are similar to each other, and step changes are rare, plus step changes tend to occur where there is an edge in the image space. And they use total variational regularization, and they use robustifying norms such as the Huber norm and so on, and various other techniques, and it actually works quite well. Back in 2011 was the first real-time dense monocular SLAM algorithm. There's been a few more since then. And then if you put these three things together, so you have the the shape from shading and building up surface reflectance model, and you have building a physics model under the visible surface. And in the SLAM model, what you have is, along with the depth map, you have a velocity map, which says that actually not everything in the scene is stationary. You can have blocks of material moving relative to each other, but the same regularization that you expect that adjacent points in the image relate to adjacent points in the scene that normally will move together, and you will have a few edges, boundaries between them. So the maths from the different algorithms all makes sense. There have been some people who have done some dynamic SLAM algorithms. They tend to first take a scan of the scene while it's static, so that they already have a mesh for the scene, and then they compute deformations of the mesh. I tend to think that that's a little bit too much to ask for the practical application, that you want to have something which, like a person being sort of woken up or stepping into a new room, it takes 2 seconds to get your bearings. So this is the bootstrap time, but you should be able to bootstrap without extra help and so on. It just takes a little bit of a modest amount of time, and mathematically it all makes sense. It should work. Somebody needs to implement it and find out what the difficult parts are.
That's super interesting. And why did you stop to do this?
When I was a veterinary student, so training to become a veterinary surgeon, I got interested in computerized medical diagnostics, and I realized that so far as the diagnostics was actually objectively true, it has to be logically valid, and on the basis of the evidence, and therefore it has to be programmable. And so I started working on this and realized that one of the things you actually need is some robotic interaction, because you need to have some data that's under the direct control of the diagnostician, the diagnostic program, so that it knows how far it can trust other sources of information. Because if you've got a team of people in a clinic or a hospital working on a diagnosis, you've got all the different stakeholders, the owner, if it's medicine, then the patient themselves, and the staff in the hospital.
Yeah,
they should all know that they should not do this, but they always do, which is that they have their own favored theory as to what the diagnosis is, and then they try to skew all the information in favor of their preferred theory.
Okay.
This is why any diagnostic program has to have at least some sensor data that it has direct control over, and that basically implies that it has to have some robotic interaction. Now, that was in the 1990s, and the internet was a bit primitive, and I was having trouble finding out who was doing what. Gradually, the internet improved, and I discovered that there were already these people called cognitive roboticists who had already, coming from the artificial intelligence side, worked out that actually they need to have some robotic embodiment in order to ground intelligence. And they were having big discussions about how wonderfully important embodiment was, but none of them actually knew anything about how bodies worked.
Yeah.
Because they were philosophers and mathematicians and computer scientists and so on. They were not surgeons.
Of course
not many people ever have reason to know what's underneath the skin.
Yeah.
And of course, the other side that you will have encountered, being an engineer working in anatomical simulation, is that 98% of people in medicine really can't do mathematics beyond high school level.
Yeah.
Even their knowledge of things like the physics of mechanics and so on is really very naive. And it takes a few people that have actually lived and worked in different sides that can actually put the two sides together. So I did my MSc. It was called Evolutionary and Adaptive Systems. They've actually renamed it AI and Neuroscience, which gives people a better idea as to what they're actually doing. And then I did my PhD in mechanical engineering on the material and mechanical emulation of the human hand. So actually going and searching for what materials can I combine to produce composites that reproduce the mechanical properties of anatomical tissues, and how can I actually lay up those composites so that they reproduce anatomical structures and mechanisms, like ligaments that are anchored into bones, and ligamentous joints that actually work mechanically. And of course, what you probably noticed is that apart from highly anisotropic fibrous tissues, the body has a lot of extreme hyperelastic tissues that experience extreme shear strains. So when you look at the back of your hand and move your fingers, and you realize that all of those tendons are sitting in a continuous elastic gel, connecting them to the skin above them and the bone beneath them, and yet they're able to move without being caught and so on. And this is due to hyperelastic shear, not due to two separate objects, one sliding over each other with dry friction or a viscous fluid between them. And then there's interesting mechanics as to how those tendons are stabilized, because you actually have three sets of, three different classes of ligaments in the musculoskeletal system. We have the articular ligaments, which connect between the bones of joints, which most people are aware of. And then you have what are known as the retinacular ligaments, which hold the tendons in their paths. And there's an interesting thing that you see there where sometimes you'll have ligaments that will insert into a tendon. So if this is the tendon, the ligaments will insert actually into it, but there will be a layer of elastic tissue above and below. So when the tendon moves, the ligaments move with the tendon, but the ligaments mean that the tendon can't move side to side. It can only move in its correct path. And trying to model that in a simulation, how do you do this? And that's why I moved to wanting to do smooth particle modeling, because it's basically it's to do with the collisions between particles, and the algorithm involves finding out which particles are neighbors in each major time step anyway. This means that you don't suffer the problem that you would get if you tried to do that hyperelastic shear in finite element models, where you would basically distort the elements so far that they become numerically unstable. And yeah, it's kind of amusing to watch a finite element model explode on the screen, but it's not useful as a simulation.
Of course.
Although I have since learned that there are plenty of numerical instabilities that do affect smooth particle models as well. The clumping instability being one of them, and the problem of working out what orders of magnitude the repulsion between particles should be, the viscosity force between particles, the surface tension force, if you're including that, and then to get the springs operating in the same order of magnitude as the particles. And then when the tissues that you're trying to model may differ by orders of magnitude. I mean, obviously the modulus of the collagen fibers in a tendon or a ligament is several orders of magnitude larger than the modulus of the elastic matrix, which allows them to actually move relative to their surroundings. And finding the window of numerical stability in which you can actually make the simulation work has been part of what's taken up my time in the last 6 months or so.
I can understand why.
Sorry guys, I'm back. So we can maybe talk in a bit more generally. Maybe you already talked about it, but about how you would see actually things, Nick, for the months to come. What's a bit your plan of? I don't know if you have some development plans and so on. That's
I possibly have development aspirations and wishes, things that I hope to do. At the moment, I don't yet have a definite plan beyond the middle of July. I would just say that I don't have a job, but I have 2 job applications. My initial plan was actually that I've got savings from the last 3 years' work, and I was going to go and rent a flat in the Highlands of Scotland and work, dedicated on the code that I want to write, and then when I run out of money, start doing locum work as a veterinary surgeon. Do you know what the word locum means, or do I need to explain that?
Local?
Locum. It's basically a temporary doctor.
Okay.
So when a clinic needs a vet for 3 days to cover somebody's holiday or something like that, that's locum work. So it's temporary work. It's actually a very big activity in the healthcare sector. So doctors, veterinary surgeons, nurses, and so on often work that way because the service requires it to provide 100% service to the public. So that was my sort of fallback plan, but I have actually submitted 2 job applications, one to European Space Agency Advanced Concepts Group in the Netherlands, and the other to it's actually the Precision Livestock Farming Group in the Veterinary University of Vienna in Austria, because they had positions on offer that were potentially capable of fitting with what I wanted to do. So I will find out what happens. So
I'm actually looking because this morning I saw a guy who is I don't know exactly what he is, but he's some kind of, that's the post. The post I have, it's actually a Facebook post, and it's all in French, so I write it, but it won't be very useful. But it's because they have opened some apparently advanced veterinary center in East part of France, and I know that the INSIBO company for physics simulation will be one of the partners. So I guess they could be interested in mixed veterinary.
Just say it in French.
Veterinary field, and both simulation mixed together. It's actually it's actually a topic that I've been pushing to the Infinitec 3D company, the development company of SOFA, because that's actually a field where simulation is quite non-existing, and where there is actually more and more people that would like to have some virtual training stuff before training on animals, and and I found that interesting. It's something I don't know how needed it will be and so on, but so first, I think the field is interesting, and second, here that there was this veterinary center creation. I don't know exactly when, I don't know exactly why. I just noticed that earlier this morning, so I could check out a bit in more details if you'd like.
Yeah, and send it me and I'll read it. And the east of France, does this mean in Rhône-Alpes or in?
No, it means
further north.
No, it would be it's a bit further north. It's in Lorraine. Lorraine, it's close to actually where we are here. It's next to Alsace, and okay, that was just for information, because I saw that, and also that just to stress that it's definitely something I think which is of interest for us to consider in the simulation field. Regarding the development that you said first, it's why I'm asking is just as you understood, it's just for highlighting things in the roadmap, saying there will be people. I think there will be people working on this and this topic, and I think it's important, especially addressing the topic, a different topic like SPH, which is not tackled a lot in the community. Could be interesting to just point it out in the roadmap, saying it's not one of the main task where we ensure you that there will be a result by the next 6 months. But that's actually what we already did last time. I think I can find you the page again of the roadmap of SOFA roadmap, and you should, if I remember correctly, it's something that we already added last time, so we could just keep it. Let me check. Yes, it was here. Down the page here, it was on the more projects, because it's actually the area where, I mean, the area where we describe projects that have no insurance, where we do not set insurance that there will be progress because we are not directly involved, or we have no insurance from the researchers. There will be, they will have enough time or enough money sometimes for pursuing that. But I think it's worth, highlighting it, because maybe there will be people interested in joining. So there we could I don't know if you have a GitHub account or stuff like that.
Yes, I have GitHub.
I think since you've get connected to the Gitter as well. What I meant is that we could, for instance, set up if you have for instance a contact on this GitHub account. It could be interesting to point out your GitHub account from this page, saying, that's Mr. Hawkins, which is working on this topic. If you want to connect to him and to see if you're going to get some feedback and some things during the next 6 months about it.
Right. Yeah.
Anyway, new approaches like SPH for us, it's quite interesting because it's, as you understood, not unusual because it's not the right term, but it's really something not investigated a lot, and though it could be of interest of, as I said, several people. So
I'm very keen to be able to to increase the spatial resolution of the simulations that we do, because as a surgeon I know that the fine detail of what you simulate is actually very important for the surgical realism. And of course, this problem of how to simulate the fibroelastic tissue that I was discussing with Jean-Nico, there's actually the reason for using springs on SPH is that the springs give a good way of emulating the collagen fibers in anatomical tissues, like ligaments and tendons and so on. And then the SPH means that you can have hyperelasticity without getting numerical instability on the overly distorted finite elements. Now, increasing the resolution essentially means using a big, powerful GPU in the first place, and B, using several big, powerful GPUs. But it did seem to me that it's possible to use multi-GPU for other parts of SOFA as well, and it would make sense to do that. Although that's supposed to be the after 11 o'clock discussion, I guess.
Yeah, I mean, I think we can. Yeah, as I said, the only team which is, or I would say even the only subgroup which is really involved in GPU computation currently is the one from Adrien Courtecuisse, who was there shortly a bit yesterday to talk about matrix assembly. But
is
first,
it Adrien that will talk at 11? Or?
No. It actually, here, the topics that we set for today, for this last STC day, it was really proposals from people who registered, namely here Nick, for both SPH and multi-GPU simulations. And the idea was to see if if there was interest of others, like to come and talk as we're doing on specific topics. And that's actually two topics where we had, or especially on GPU, we had people active years ago, but finally those last years, not that much. And especially, so that's what I wanted to highlight, but not to stress that too much in the main room earlier. But it's really a topic where there is still people using single GPU computation. part of the computation which is distributed over one single GPU using the SOFA CUDA plugin. That's the basis, SOFA CUDA. But then all the code, which is actually the efficient part for FEM, for building efficiently the matrix, the stiffness matrix, and this part is done on GPU. Plus they are also using solvers on GPU. This part is private. I mean, those codes, they are private. I tried. It was 2 months ago, with the main researchers involved in this institute. There was not Adrien, but to stress the point that we needed to output those codes open source. It does not seem to be a priority, because actually the researchers I talked to for this meeting are not using it, and are not the one really using it, and so on. So I'm a bit concerned, because it would be of use of a lot of people, I think. And today it benefits to be very schematic. It benefits one.
Right.
So on my standpoint, on the SOFA standpoint, it's a waste, a huge waste, because it's not well maintained. It's not helping a lot of papers. So I'll see how to push it. I'll see with maybe more on the administration part, like trying to say, hey, you, the research institute, you are wasting your, because when a code is not open source, what it means on the long run, it means that at the end it ends in the trash. That's what it means.
Exactly.
So, and that's really my fear, because it's a code that still, I mean, it's not. Now it's state of the art, even a bit less than state of the art. I would say GPU computing is not. It's hard now to make a paper about GPU. Super hard. You cannot just say, "Oh, I made that on GPU." No, that's not enough. You need to have a huge scientific contribution on top of that. So I really think, for this reason, this plugin should not anymore be and those plugins, because plugins for solvers, for constraint resolution on GPU. So all that should be opened.
What I was seeing with the Phoenix talk yesterday was that so that actually outputs C kernels for an element, and he talked. So then you wrap that in a for loop to go over the elements in the model, but it seems to me that you can probably wrap that in GPU kernels. And therefore quite quickly write solvers for GPU that way.
We did that actually 5 years ago to get, it was based on XML format, where instead of Python here, the proposal of Phoenix it was based on Python, Python based language. It was an XML based language that was interpreted, that was generating some actually C++ code with a GPU kernels associated automatically. It was simple kernels, but still it means you're creating a new force field that by default can be parallelized on GPU if you like. So yes, I think it would be. I don't know if Stefan is already thinking about it, because it's not really things where Stefan is actually mostly interested the GPU part. And it's also because he does not himself has a lot of experience, I think, with GPU, especially GPU. I mean, coding kernels. But I think today there is no one in the community, and here I think I can really say almost no one who knows really modern kernels of CUDA, because I think we are underestimating a lot the progress that has been made.
I think that we should actually be looking at SYCL for the host code and OpenCL kernels on the GPUs, and the reason for that is that what has now happened, people were expecting for the last 5 years. Now Intel and AMD have got GPU processors that are competitive with NVIDIA, and the next generation of clusters and supercomputing workstations and so on are no longer exclusively NVIDIA. They are the fastest computer in the world, the first exaflop cluster at Argonne National Laboratories in the United States is using Intel GPUs. And they're using essentially SYCL with some extensions from Intel for that. But and also we're seeing the C++ standard basically moving towards parallelism. So in C++ 17, we've already got parallel STL as part of the C++ standard. And this is intended to make it easy to parallelize things. And Kronos SYCL have got their implementation of the parallel STL. So it should all flow together. And the nature of the simulations that we're doing are overwhelmingly data parallel and therefore suitable for it. But as you say, we don't want to disrupt the stable core of SOFA. We want to do this in a plugin, and when there's enough of it working, then it may get adopted and become the new way. So I've sort of coming away with kind of a sketch of A, what needs to be done, and B, how it might be feasible with minimal actual programming resources to achieve that. Partly what I need is to see what happens with SOFA NG, and to be basically targeting my plugin as something that will plug into SOFA NG rather than into existing SOFA. I can get a version 1 of my morphogenesis plugin to plug into existing SOFA so that people can actually use it and so on. But that's a single GPU CUDA code, and then when I rewrite it as multi-GPU and OpenCL SYCL, that will be part of a larger parallel SOFA plugin for SOFA NG.
Yeah, and that's a good way to go. What is mostly, I think, in the first step is indeed to make something available that many people can actually use and easily use. So as a plugin, and indeed the best way to work is actually to have that integrated within one of the release of SOFA, one of the binary version of SOFA, so that at that point you say, oh, this is here, I made a plugin. You can compile. For instance, we could help you providing binaries of your plugins and saying, those binaries, they are, and it helps a lot distributing.
And it then also has to include demonstration models to show people what they can do with it, and documentation telling them how to, and so on. I noticed that with the multi-material tools that I made for generating partitioned finite element meshes, was that there were, I think, 2 people were interested in the first 6 months, and then I haven't heard anything since. And I really, if I'd had time to write a SOFA GUI, and so people can just do it with the mouse in the GUI, then I think there may be more uptake. But also crucially, if I had some interesting models that were built that way. So if I had a heart that would beat for them, then they would be really impressed with it, and possibly people will go for it. But as it was as command line tools and text telling them, if you read this text, you can find out how to do this, that didn't really draw people to it at all.
Definitely. You took the heart example. Yeah, definitely that would be I mean, you know, when you make one kind of striking demo, that would definitely attract people. They would, especially if you have the piece of code that can be tested straight away.
It's always the demo.
Always the demo. Yeah.
You need to sell it.
Yeah. So for that, what I suggest is really to highlight that on the roadmap page. As soon as you have some you know, even if it's the video you sent me, it's really a question of when you want to communicate about your work, even if it's not fully ready yet or whatever, but just to start talking about things. Just let me know. We can you know, make some videos. We can make some advertisement, and that's the way it goes. I mean, the way it works, the codes that are actually attracting people and coming for questions, for collaborations and stuff like that are things that we do communicate about. Obviously, if we don't talk about it, it's just a repository and we never promote that anywhere, or just very silently. People are not finding the especially companies and so on. They are rarely finding their way through the GitHub repositories. Oh, we're gonna break out in 1 minute. I just saw that. Okay. But yeah, it would be really to keep us both updated within the next months, and just see what comes from that. I could already talk a bit about the video you sent me before the technical committee. It's really up to you. Just let me know how you want to run things. And
yes, I think if you show people the video, and then I can sort of explain what's going on, that although what they're seeing as a spring mesh, there is also SPH behind each of the particles, and how I'm producing anisotropic tissue by mechanical deformation.
Cool. Let's do that. Okay, I think we're going to be dropped in the other room in a few seconds. Okay. And back again. So yeah, it's definitely the continuity of what we were saying here. So it's more or less actually it's even a bit the conclusion of the discussion. So you were saying, if I understand properly, it would be maybe for you more interest. You think it would be more interesting to go for an OpenCL implementation because more generic, right?
Yes. For a long time, there was the problem that although OpenCL was supposed to be the portable one, NVIDIA were avoiding supporting it more than necessary, even though NVIDIA were the chair of the OpenCL Standards Committee. The obvious commercial reason is that they had a strong advantage in CUDA and they didn't want to lose it. However, now there are multiple compilers available that can ingest OpenCL SYCL and run on NVIDIA, and do so with good efficiency, so that they're running at least sort of 80–90% of the efficiency of a NVIDIA version. And the main way they do this is by generating CUDA PTX. So the OpenCL kernel goes to LLVM for compilation, outputs CUDA PTX, and then sends that to the NVIDIA runtime. And there's nothing that NVIDIA can do to spoil that won't spoil CUDA.
Yeah, I see.
The other thing is that a key advantage of the OpenCL kernels is that you can also run them on the CPU, which means that you can actually have good debugging access. Whereas when you're running things on GPU, you can't run a debugger in the GPU itself, and that's a big issue when you have something complex. And it also means that you can adapt to a wide range of different computers. So I'm talking to you on a Dell Latitude. It has a Core i7 in it, and the Core i7 CPU includes an Intel HD intrinsic GPU. That GPU has 30 times the flops rate of the CPU, and that's on a little notebook laptop. It's not a GPU laptop, but it still would run a faster, more complex model if it were running on GPU than if it were running on CPU. But the trick really with parallelization is you have to avoid incurring additional overheads, because otherwise the costs of parallelization outweigh the potential speed up, and you lose the.
I mean the cost to send data on the GPU. That's what you mean?
Yes, so it is. So basically, parallelization optimization is dominated by managing the data flows. So the first and slowest one of all is moving data on and off an extrinsic GPU. This is a slightly different with an intrinsic GPU that's actually on the same chip as the CPU, because they're actually still using the same low-level cache, and the large RAM is the same large RAM. It's not a separate DRAM on board the graphics card. Moving data on and off the GPU is the first big slowdown, and the second big slowdown is disorganized read-writes. This is why in particle models you always have to sort the data. A problem I had to deal with was that there was supposed to be an OpenCL SPH code written by a PhD student whose PhD I'd arranged in Bath. And he was supposed to be copying the algorithm from Fluids version 3, but he misunderstood why the algorithm did things the way it did, partly because he was working with engineers but not with computer scientists, so he wasn't taught about optimization and how it works, particularly for the GPU. And what he did is he sorted the pointers to the memory, but the data was still disordered. And what you got was this this code runs fine when you have 1,000, maybe 4,000 particles. If you try to scale up above that, it just hits this exponential wall. It will not run. And so it's very easy when parallelizing to get the spelling and pronunciation wrong and simply parallelize your code. And that's also why what piecemeal acceleration doesn't necessarily make that much of a useful difference, because if you've got this one thing that you want to accelerate and you move that onto the GPU, then you have to move it back off again, and you're doing this every time step. And then you have a second thing you want to accelerate, and that means you're actually moving the data back and forth between the GPU and the CPU twice every time step. And that's very undesirable in terms of the slowdown that it causes. Whereas if you can write code that the data structures are data parallel, the functions for processing the code are data parallel kernels, those can be run on the CPU if that's what the computer you're working with at that moment has, but they can also be run on GPU or on other accelerators depending on what becomes available, because there's some exotic varieties that people are playing with and may become more significant. So if the data is structured that way and the algorithms are explicitly data parallel, then whenever the hardware you're running it on is suitable for that, you can move the data so that it is then native to whichever processor you're going to run it on, and you only move data on and off that you absolutely need to. So the user's instructions go in, and the graphics and the haptic feedback come out. And it's similar in fact, to the way that you balance loads between multiple processors, that what you're looking for is the smallest amount of communication needed between the processors. So in particle models, you tend to do your coordinate bisection in order to divide the simulation space so that you have equal numbers of particles on each processor, and an interface, a plane that cuts the simulation space so that you have the smallest number of particles actually crossing between the two processors. I think that with finite element models, of course, you're not having to sort every time step, because the mesh remains ordered unless you are remeshing for other reasons. You may have large plastic deformations and so on, and also there's cutting and so on. But the scene graph still tells us a lot about what the data exchange between the different objects within the simulation actually is. And so it gives us a very clear guide as to how the model can be broken up across multiple processors. And obviously the first implementations would be static manual divisions across processors. So you'd say, I'm going to be running this particular simulation on this particular quadruple GPU workstation, for example, and therefore I will place these things on into these processes which will live on these processors. So if I've got 4 GPUs, I'll probably have 4 MPI ranks that are managing those, and then a master rank that's running only on the CPU that's the overall controller, and is running the GUI for the user.
So to understand what was, more generally, it means you like to really write your first kernels for directly in OpenCL, so there would be no link to CUDA since the very beginning, right?
Yeah. So well, the morphogenesis code that I have at the moment is written in CUDA because I needed to get started quickly. But that yeah, essentially we for our future parallel sofa plugin, basically all of the functions which operate on the data would be written as data parallel kernels. They would be written as OpenCL kernels, and the host code that manages the launching of kernels would be written in SYCL, because then regardless of what computer the user wishes to run it on, it can use the hardware that's there. And so if you've got somebody who's got a big powerful AMD Threadripper CPU that has many cores, you could vectorize stuff on that CPU, still using the same kernels and same data structures in OpenCL. And then somebody else will have a laptop like my current one that has a single NVIDIA GPU in it, and it would be able to run on that, and it would basically move all its data structures onto the GPU and send it to the kernels there, because the new generation of compilers for OpenCL SYCL can output CUDA PTX. They should be able to send those kernels to the NVIDIA GPU and have it run, and run almost as well as if it were written in CUDA, but without the labor of writing 2 different families of kernels.
This is definitely super. I think super interesting for and this CPU compatible platform independent approach. It's I think really powerful. It's we do have as well a OpenCL plugin. This one is really inactive for a long time, so I don't know if it's still really up to date, and if not, how much work it would be needed to make it work. This is the first concern, and the second one was to know how you would see on a I would say, you know, physical system matrix resolution standpoint, on the resolution standpoint of your meshless problem. How would that? Do you have your own solver already? Would that work to incorporate that into some existing Sophos? Not one, maybe with any Sophos solvers.
Okay, so the way my system works is, so essentially I have my buffers, which are the arrays. So essentially you try to arrange it so that you have a struct of arrays arrangement, because that's how you get the it's one of the steps necessary to get the ordered read writes when you've got several thousand GPU cores reading consecutive particles in the array. Then you get a nice ordered read write, which is fast and efficient. And then I have a sequence of kernels, and they perform the operation. So the steps in SPH are, first you have to sort the particles to find out which ones are actually adjacent to each other. Then you compute the pressure, and that means that for each particle you find the other particles in range, and compute the pressure for the particle that calls the thread. Record that in the buffer. Then the next kernel computes the force between the fluid force between the particles on the basis of the pressure in each of the pairs of particles that are interacting. And if it's just pure fluid SPH, then the next step is to move the particles. Because I also have other things. I have my diffusion kernel, and then I have my epigenetic kernel that actually does computes the genetic network for each particle to see how it's going to behave, and then I do my remodeling, which is again two steps. First is the bond remodeling, and the second is the particle remodeling. Because several of those kernels of my additional kernels there will only run on 1% of particles in a given time step, what I do is I actually have two additional sortings of particles to produce dense lists for those kernels, so that when those kernels are called, they're called only for the particles that they're going to be operating on. And that keeps my my code actually quite compact and fast. So at the moment, for example, in simulation that that's in the video, it's still dominated by the fluid force interaction as being the main thing that's actually taking time to compute there. The springs are actually not taking up very much extra time to compute, because there's only 3 of them per particle, and because in the sorting I'm keeping track of basically because springs belong to a particle, and when the particles are sorted, it also keeps track of where the other particle at the other end of the spring is. It means that when it's time to compute the force, it doesn't actually take very long to do that computation. I'm losing my thread here. So that's kind of the sequence. So essentially, it's this data structure of a structure of arrays, and then a sequence of kernels that get called. Some of those kernels are sorting particles, so that additional kernels are only called for those particles that are required. I'm not sure how that maps to the SOFA model of having a separate solver.
Yeah, because as you said, I think I see from what I understand, it's mostly a compact code where you can compute the spring forces, the particle forces, but on the solving part, it still seem all packed together.
On the which part?
On the solving part, you know,
on the solving. Yeah, I mean, it's essentially the so you have a compute pressure kernel, and you have a compute force kernel, and then an advanced particles kernel.
Okay.
They don't really do anything other than that. I don't know, it doesn't seem to have a concept of a solving separate to those kernels.
Okay. And because I guess here you're going to have some of the I mean, you're going to have some explicit forces here, and you might have as well. I don't know if you have some. So you might have some mass particles, or are you making only static simulation for?
Each particle has mass. It is possible to have the mass change. The main reason I do that is that you have tissues of different densities in the body. So, for example, bone is more dense than most of the other tissues, and you might wish to actually give it mass and that is different to correctly reflect that. Yeah.
Okay, but on the system, so it means, because you said the mass can change, but so there is a mass matrix, or what we could that could be computed from that, right?
Yeah. So what there is there is an array or a buffer of masses for each particle.
Mm-hmm.
And yeah, so in that, partly it's because not being conceived as a matrix, because the computational efficiency depends upon having the data sorted so that you've got essentially the you do a bin sort on the particles. So the sorting works with 3 consecutive kernels. The first one is insert particles, which goes over each particle, does an integer divide for on the position of the particle to find out which bin that particle has to go into. It records in that particle's data the bin it goes into, and in that bin it does an atomic add 1 particle to the count for that bin.
Mm-hmm.
And it reads the new count for that bin and writes that to the particle, says that this is now the position of this particle in the bin.
Regarding the scheme, the integration scheme, and at the end you should always, I mean, you have to end up with a linear system that you all solve, right?
In the advanced particles kernel, which is at the end of the time step, the integration for deciding how the particle moves, having calculated the force on the particles, that's a leapfrog integration there, occurring in that kernel. It also includes the simulation boundary calculations in the same kernel, because obviously it has to bounce off the walls.
Because the interest why I'm asking the question is because I'd like to what I would find nice is actually to see these methods actually fitting as well the usual SOFA API for designing. I mean, for designing and solving a system,
right?
Because having if you have some kernel following any scheme like Leapfrog or any others, but for OpenCL, it means it would not only work for particles, but it would as well work for anything else, right? The part of solving is could be pretty independent from the rest, and that's why I was asking that how much actually fit the SOFA API, so that maybe these parallelized versions could also benefit others on even other application and other methods than SPH. That was just a thought.
It's essentially I've taken the code of Rama Hodson, who's the guy's name I couldn't remember earlier, the author of Fluids version 3, taken his code because it was it was and still is the fastest SPH code, and I've basically adapted and extended that to do the extra things. So I'm sure that the design of this has been designed around the need to produce a fast GPU-based SPH. I haven't had time to try experimenting with what happens if you change that and so on. I've basically been making the changes necessary to add the features that I want in the morphogenesis. Making it more of a SOFA paradigm implementation would require some thought, I think, on my part.
Yeah, definitely. But it's just, I think, it could be a nice, step, or at least to keep this in mind.
Yeah, I suspect that a certain amount of how Rama wrote this code is important to why it works so quickly, and why it's possible to run 1 million particles in real time on a single GPU. And of course, that resolution is quite desirable in terms of having a useful simulation for surgical simulation, but also for machine perception purposes and so on, and all manner of other things that people want. So perhaps the sort of the eventual solution is to work out how you can express things in the source code in the SOFA paradigm that allows you to change out which solver you use and so on, but so that it actually generates executable code that is very close to how Rama made his code work so fast.
Yeah, I can see him. Again, it's just because I like to see things, I would say, really integrated in terms of following the same pipes as the SOFA pipes. Otherwise, we might have. I mean, otherwise, I think objects in the same scene would not really interact if they are not following the same API for resolution.
I mean, my existing way of having an interaction with the thing is to have certain special particles whose motion I have a separate kernel for that says that these particles are static, so when it comes time to update their position, they just get their old position written back to them, and then these particles are actually going to be moving on this particular trajectory, so they get that trajectory written to their position. And so my first way of connecting to other SOFA objects would be to use those particles as the collision interface. I think that it should be possible to have a triangle mesh or a surface mesh composed of facets interact with particles in an SPH model in much the same way that the boundaries of the SPH simulation interact with the particles. And that should be implementable with, you'd need to do a sorting of the facets so that you know which bins those facets are present in. And then you'd need to do a force interaction between facets and particles to impart force on the particles, and also to send the force on the facet back to the rest of the SOFA simulation, so that it can interact with the finite element mesh and anything else that people might have.
Mm-hmm. Yeah. Okay. Okay, so regarding the multi-GPU, again, here I think this has never, there have been work on grids, there have been work, SOFA simulation work on clusters, whatever, but multi-GPU, I think it has almost never been a raised topic in the community. So that could be interesting. I mean, if you dig a bit the topic, it could be interesting to make a short feedback in the next 6 months. I mean, in 6 months, for the SOFA week, there will be at the SOFA week there is always a bit more people, especially. So there is the scientific day, and there is as well the more technical day, which is related to implementation, as we are talking today. So that would be, I think that would be nice, a nice meeting up again for that topic, if you agree.
And I will be in Europe, and I will hopefully be vaccinated from COVID by that time, and we may actually have a face-to-face meeting on that occasion. I don't know. It depends on what happens.
Actually, for the moment, we schedule to make it fully online again.
Okay, right,
just because I see too many events. I'm not talking about previous months, I'm talking about upcoming events that are actually making the decision that it's still for up to the end of the year too complicated, or not too complicated, but too risky in terms of success. But at least what it will help a lot, it's that since you'll be on the same schedule, you're going to be, without staying awake for way too long, available, and that will, I think, help a lot.
Last night, 6 p.m. France time, 5 p.m. UK time, I was trying to watch a surgical robotics lecture happening in London, and I fell asleep.
I mean,
I just woke up on my sofa, and it was like, oh dear, I've missed that.
What time does that make? For instance, right now for you, what time is it?
Time here in Brisbane is 7 p.m.
Okay. So it's still reasonable, but Okay.
Yeah.
It means it's really, I mean, it's the same for people, for our colleagues in South Korea. They are always
they're essentially the same time zone, or near enough.
Available in the morning, but for the afternoon it's too complicated.
The confusing one is if you're in Australia or East Asia talking to people in the United States, because it's almost always a different day where they are.
Yeah. And it's then it means that for you it's usually what is that? It's you can't make meetings in the morning because it's night for them, I guess.
So if we talk to somebody in the United States, particularly if it's California and so on, then we would be staying up late here, and is that right? No. So we would be getting up early in the morning to talk to them, but they're living in the evening of the day before.
Yeah, I see. Okay. So I think this will help, and I think it could be a good a good occasion to meet. Do not hesitate to keep me as well updated about first videos as you did, but even you know, if you found the position, one of the position you applied for could be interesting to know that as well. Okay.
Yeah. Great.
Cool. Thanks anyway for proposing the topics and as well for joining those days. What we can do, we can actually I'm going to take a few issues on the GitHub here that have been poked and start coding a bit this afternoon. I don't know if I'm gonna make it for topology. It's going to be again for you way too late maybe. But if you,
I've got another London lecture this evening, so I'm going to be staying up. So
all right.
Yeah.
Then good luck for that. What I suggest is that we can go back to the main room. If you'd like to again yourself pick up some stuff, or just if you have some other questions about stuff, do not hesitate.
Yeah.
And most importantly, let's get in touch. Let's keep in touch for the next months and weeks and months to come, so that I'm sure there will be update on your end about position quite soon. So
yes, I've got to do things like pack all my possessions into my trunks and so on, because they get collected on the 30th of June.
Yeah. So end of the month, you're moving.
Well, end of the month, my possessions are collected. So then I'm living only with my airline baggage, and then I think it's the 12th that I catch the aircraft, and then I arrive in the UK. It'll be I think it's the 14th by the time I actually arrive. But yeah.
Okay, cool. Then all the best for this period, this moving period, which is always a funny time. And let's keep in touch. Okay, let's move to the main room.
Yes, great.
Let's go.
Thank you very much.
Thanks.